Hello, students. Hello, and welcome to this new chapter of binomials, multinomials, and expansions. In the previous video, we finished mathematical induction. So, if you look at the chapters, we have covered logarithm, progression, complex number, polynomials, permutation, combination, combinatorics, that is mathematical induction. 6 chapters we have completed. We are starting 7th chapter, then we have determinants, matrices, and miscellaneous problems. So, as always, the theory is going to be quite important because while solving problems, you will face difficulty if you are not clear with the theory side of it. Okay, so we might take maybe 2 videos to cover all of theory, and so today and tomorrow we'll try to cover as much as we can. We should be able to finish theory in 2 videos. And the link to download the PDF will be in the description, as well as at the end I'll show you both the books links as well as the question answer website where you can come and ask questions. So without further ado, let's get started. Mostly I'll read through the theory so you can pause and read on your own. An algebraic expression containing one term is called monomial. 2 terms is called binomial, and more than 2 is called multinomial. Examples of monomial expressions are 2x, 4y. Examples of binomial expressions are a plus b, x squared plus y squared, x cubed plus y cubed, x plus 1 upon y. And examples of multinomial expressions are 1 plus x squared, a squared plus 2a plus b squared, a cube plus 3a squared b plus 3ab squared plus b cubed. So a fact you have to observe here is a squared plus 2ab plus b squared is actually a plus b whole square. Okay, so a plus b whole square is a binomial, but the expansion is a multinomial. Similarly, this is a plus b whole cube. So the cube one is binomial, but the expansion is multinomial. Now we will touch upon the most important theorem of this chapter, that is binomial theorem. Newton gave binomial theorem by which we can expand any spelling is wrong power of a binomial expression as a series. First, we consider only positive integral values as exponent. For positive integral exponent, the formula has the following form. So as you know, we have encountered many problems where we have used binomial expansion. So after this chapter, you can go back and solve those problems if you skip those. So the expansion is given by if the binomial is a plus x raised to the power n is equal to nc0 a raised to the power n x raised to the power 0 plus nc1 a raised to the power n minus 1 x raised to the power 1 plus nc2 a raised to the power n minus 2 x squared, and so on up to ncn a0 x raised to the power n. Now we will prove this by mathematical induction. Let this be P of n. Now when n is equal to 1, our left hand side is a plus x and right hand side is 1c0 a plus 1c1x. That is true for n is equal to 1. For n is equal to 2, left hand side becomes a square plus 2x plus x square, and right hand side becomes 2c0 a square plus 2c1x plus 2c2x square. This needs to be fixed. This is not good. Thus, we see that Pn holds good for n is equal to 1 and n is equal to 2. Let Pn do true for n is equal to k. That is a plus x raised to the power k is equal to kc0, a raised to the power k, x raised to the power 0, and so on. Now we multiply both hand sides with a plus x. Left hand side takes the form of pk plus 1, and right hand side becomes kc0, a plus raised to the power k plus 1, x raised to the power 0 plus kc1 a raised to the power k, x plus kc2 a raised to the power k minus 1 x square, and so on up to kck a x raised to the power k plus. So all the terms here were multiplied by a. Now we multiply by x. It becomes kc0 a raised to the power kx plus kc1 a raised to the power k minus 1 x square, and so on. So now what we will do is we will take this same power akx and akx and we will add that. We will write kc0 as k plus 1 c0 and kck as, this kck as k plus 1 ck plus 1. And we will use the formula mcr plus mcr plus 1 is equal to n plus 1 cr plus 1. So we combine this with this, we get k plus 1 c1. So we have this and we have this, as I said, we have this. Similarly, adding the power of k minus 1 x square, we have 2 plus 1 c2. So we see that P of n holds good for n is equal to k plus 1, and hence we have proven the binomial theorem by expand and induction. Now we will prove by combination. A plus x to the power n is equal to a plus x times a plus x times a plus x. There will be n such factor. If I don't know what has to be seen here. We look at the powers of A. Okay, we see that a to the power n exists, and a to the power n is a term of the final product. This is the term a raised to the power n, which can be written as nc0 a raised to the power n x raised to the power 0. If we take the letter a comma n minus 1 times some x ones, then we observe that that should be corrected. X can be taken in nc1 ways. Thus, we see that the term in the final product is nc1 a raised to the power n minus 1 x. Similarly, we choose a n minus 2 times and x twice, then the term will be nc2 and a raised to the power n minus 3 x square, and so on. Thus, we have proven the binomial theorem by combination. So this should be that if we see only A, okay, there should be a V. Now we have special forms of binomial expansion. This is what we have proven. We put x is equal to minus x, a minus x to the power n is equal to this much. And we put a is equal to 1 in this expansion. We have got 1 plus x raised to the power n is equal to nc0 plus nc1x plus nc2x square, and so on. We put x is equal to minus x in this equation. We have got expansion of 1 minus x raised to the power n, and so on. Now we look at the general term of the binomial expansion. The general term is the observation. We see that is ncr minus 1 a raised to the power n minus r plus 1 x raised to the power r minus 1. Now we look at the middle term of the binomial expansion. If n is even number, then n is equal to 2m. The middle term will be m plus 1th term. When n is equal to 2m, there will be a total of 2m plus 1 terms. So the middle term will be m plus 1th term. That is equal to ncm a raised to the power n and c nx in power n. When n is an odd number, that is n is equal to 2m plus 1, then m plus 1h and m plus 2h term will be middle term. So those terms are ncm a raised to the power m plus 1 x raised to the power n and ncm plus 1 a raised to the power n x raised to the power n plus 1. The middle terms are the largest quotient. Note this fact, the middle terms are the largest quotient. In case of two middle terms, the quotient of both the middle terms are equal. So see here, n is 2n plus 1, so 2n plus 1 cm and 2m plus 1 cm plus 1 both are equal for equal quotients. Now we look at equidistant quotient. Binomial quotient equidistant from start and end are equal. Pay attention to this fact. Okay? Quotients of first term from start and end are nc0 and ncn, which are equal. Quotient of second term from start and end are nc1 and ncn minus 1, which are equal. Similarly, quotient of first term from the start is ncr minus 1 and from the end is ncn minus r plus 1. From combinations, we know that ncr minus 1 is equal to ncn minus r plus 1. Thus, it is to prove that it should be proven that quotient of terms equidistant from start and end are equal. Now we look at properties of binomial quotient. We have 1 plus x raised to the power n is equal to this much. So we put x is equal to 1. We get 2 raised to the power n is equal to sum of quotients. Now this we have used a lot of times in our examples or problems. We put x is equal to minus 1, left hand side becomes 0, and right hand side becomes this. Okay. Adding these two, this one and this one, we have what? 2 to the power n is equal to 2 times nc0 plus nc2 plus nc4 and so on. There is an equal sign missing here. 2 cancels 2 here, so it becomes 2 raised to the power n minus 1 nc0 plus. There is something wrong here. Okay, so this I believe is a subtraction. Okay, subtraction we see this, not subtraction. Let me see. So this is this. Okay, on adding we have got this. But this I think is we need to discard this. This is of no consequence. So we have got 2 raised to the power n is equal to 2 nc0 plus nc2 plus nc4. Now we subtract these two, we get 2 to the power n minus 1 is equal to nc1, nc3 plus nc5 and so on. So here what possibility is that you cancel 2, you get 2 to the power n minus 1. But this is wrong. This should be nc0, nc2, nc4, not 1 and 2. I'll fix this. Okay. Now we look at multinomial theorem. Consider the multinomial when typing mistake here. X1 plus x2 up to x to the power n to the power p, where n and p are positive integers. The binary term of such a multinomial is given by p factorial upon p1 factorial times p2 factorial up to pn factorial times x raised to the power x1 raised to the power p1, x2 raised to the power p2, and xn raised to the power pn. First, that p1, p2 up to pn are non-negative integers, and p1 plus p2 up to pn is equal to p. We can find the binary term using the binomial theorem itself. Binary term in the expansion x1 plus x2 plus x3 up to xn raised to power n is. Here we convert the multinomial into binomial. One term is x1, another is the remainder of that. So the binary term in the expansion becomes n factorial upon p factorial, which would be p1 factorial, times n minus p1 factorial, x1 to the power p1, x2 plus x3 and to xn is equal to n minus p1. So this should be p1 factorial. Okay. Now general term in the expansion of x2 plus x3 plus x to power n and minus p1 is n minus p1 factorial upon p2 factorial times n minus p1 minus p2 factorial, x to the power p2 times x3 plus x4 plus xn raised to the power n minus p1 minus p2. Now you see that recursively you follow this and you get the general term which we have described over here. You see, if you multiply if you put the value of this over here, you will see that n minus p factorial will cancel, and the denominator will contain p1 factorial times p2 factorial. Similarly, upon proceeding in similar manner, we will have this general term. Some results on multinomial expression. Number of terms in the multinomial x1 plus x2 plus up to xn raised to the power p is number of non-negative integral solutions of the equation p1 plus p2 up to pn is equal to p. That is n plus p minus 1 cp or n plus p minus 1 c n minus 1. Largest coefficient in x1 plus x2 up to xn raised to the power p is n factorial by q factorial to the power n minus r times q plus 1 factorial to the power r, where r is the quotient and r is the remainder of p divided by m. Quotient of x raised to the power r in a0 plus a1x plus a2x up to n x raised to the power n to the power p is sigma n factorial over p0 factorial plus times p1 factorial times p2 factorial up to pn factorial a raised to the power 0, a1 raised to the power p1 and so on up to a1 p raised to the power n. Here goes into an ellipsis here, where p0, p1 up to pn are non-negative integers satisfying the equation p0 plus p1 up to pn is equal to n, and p1 plus 2 p2 plus 3 p3 up to n pn is equal to r. So I think we should stop here. Let me see how much is there. We can finish this today, but it will be best if we cover it tomorrow because a lot of thought you have to give to these calculations. Okay, pay attention to section 7.7. In particular, it is complicated, and 7.8 and 9 are very, very important. 7.8 and 9 are very, very important. 7.7 section 7.7 in particular, it is complicated, and 9 are very, very important. 7.8 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 and 9 are very, very important. 7. And remember the formulas, okay? Remember this fact here, 1 and 2. These are important observations you have to make, okay? Get acquainted with the formulas and the expansions, practice them, writing them few times, so that when we solve the problems, you don't get stuck. With this, I will end this video here, and we will meet again tomorrow with the remainder of the theory and possibly 10 problems. Okay, we can do 10 problems today, tomorrow. Not much is there. We have half page here, 1 page, and so it will be done. Tomorrow we will solve questions here. Okay, so problems we will solve. In the beginning, there will be easy problems, but slowly the problems will advance and make it. So thanks a lot for watching the video. I'll see you in the next one. Have a great day and enjoy.